Today, we're digging into a family of chemicals that are, well, a little bit of a paradox. They're both heroes and villains in the story of our modern world. They are super reactive, incredibly powerful, and, as you'll see, they are absolutely everywhere.
So, let's just jump right in with a quick question. What could possibly be the chemical link between the stuff that puts you to sleep for surgery, the pesticide that protects our food, and the refrigerant that cools your fridge? I mean, they seem completely unrelated, right? But they all share a secret chemical identity. The answer? They're all part of this fascinating family called halogen derivatives.
All right, Section 1, a new chemical family. So let's get down to basics. What exactly are these things?
The concept is actually pretty straightforward. You start with a basic hydrocarbon. Think of it as a simple skeleton made of carbon and hydrogen. Then you just swap one of those hydrogen atoms for a halogen atom, like chlorine, bromine, or iodine. And bam, that one tiny change gives you a whole new compound, a halogen derivative.
Chemists even have a little shorthand for this. You'll often see a diagram of a hydrocarbon with the letter X stuck to it. That X is just a placeholder. It can stand for any of those halogens we just mentioned. And it's that one little addition, that X, that really gives this entire family its uniquely reactive personality.
Okay, Section 2, the halogen family tree. Just like any big family, this one has different branches. So, how do we classify them?
Think of it as having two main branches. On one side, you have the haloalkanes. That's where the halogen is attached to a simple, straight, or branched carbon chain. On the other side, you've got the haloarenes, where the halogen is bonded directly to a super stable carbon ring. This tiny difference in structure, it completely changes how they behave chemically.
And from there, it gets even more detailed. It's like meeting all the chemical cousins. The exact placement of that halogen atom is everything. If it's on a carbon that's right next to a double bond, we call it an allylic halide. But if it's attached directly to one of the carbons in that double bond, it's a vinylic halide. This kind of precise positioning has a huge impact on their reactivity.
Section 3, their signature moves. So we know what they look like, but what do they actually do? Well, their go-to move, their specialty, is a reaction called nucleophilic substitution.
Now, when these molecules get into a reaction, they basically face a choice, a fork in the road. They can take one of two paths. There's the SN2 path, which is like a swift, one-shot attack. And then there's the SN1 path, a more patient, two-step plan. And what decides which path it takes? It's the molecule's own shape.
Let's break down that one-shot attack, the SN2. You have an incoming group called a nucleophile that attacks the main carbon atom, but it does it from the backside, the exact opposite side of where the halogen is sitting. It all happens in one smooth, coordinated motion. As that new bond is forming, the old one is breaking, and it forces the whole molecule to flip inside out. It's famously called a Walden inversion. And here it is, that famous umbrella flip in action. See how the incoming group attacks from behind? It forces the halogen to leave from the front, and in one single, fluid motion, the molecule's entire 3D shape just inverts. It's like a perfectly timed, perfectly choreographed chemical dance.
But the SN1, now that tells a totally different story. This is the patient two-step plan. First, in a slow move, the halogen just leaves, all by itself. This creates a flat, temporary middleman called a carbocation. Then comes the fast part. A new group swoops in and attacks that carbocation to form the final product. That first step, that slow formation of the carbocation, is the bottleneck for the whole reaction. Everything has to just sit and wait for that to happen. Then, the second step, the attack, happens in a flash. This two-step process, with this critical carbocation intermediate, is the absolute defining feature of the SN1 mechanism.
So, why have two different paths? Well, it all comes down to crowding, or what chemists call steric hindrance. If that central carbon atom is surrounded by big, bulky groups, there's just no room for a sneak attack from the back. It's too crowded. So the molecule is forced to use the SN1 plan. The halogen has to leave first just to clear a path before the new group can even think about coming in.
Section 4, the mirror image mystery. Okay, this focus on 3D shape brings us to one of the coolest,
Most mind-bending ideas in all of chemistry.
Let's do a quick experiment. Hold up your hands. See? They're perfect mirror images of each other. But now try to lay your right hand flat on top of your left, so they line up perfectly, thumb on thumb, pinky on pinky. You can't do it. They're non-superimposable mirror images. This property has a name. It's called chirality, from the Greek word for hand.
Believe it or not, the same exact principle applies to molecules. Whenever a carbon atom is attached to 4 totally different groups, that carbon becomes what we call a chiral center, and it means the molecule it's in can exist in 2 forms, a left-handed version and a right-handed version. And just like your hands, they are mirror images that you can't stack on top of each other.
These molecular mirror image twins are called enantiomers. Now here's why this is so incredibly important. Physically, they're identical. Same boiling point, same density, the whole deal. But our bodies are also chiral. Our enzymes, our cell receptors, they're built to recognize only one hand. This means the right-handed version of a drug could be a lifesaver, while the left-handed version might do nothing, or in some famous cases, could even be incredibly harmful.
So, Section 5, a complicated legacy. When you put all this together, what has this powerful chemical family actually meant for our world? Well, the answer is, it's complicated.
Let's start with the good stuff. This quote celebrates Victor Grignard, who won a Nobel Prize way back in 1912, and his prize-winning discovery, a revolutionary new chemical tool called the Grignard reagent, which was made from, you guessed it, a simple halogen derivative.
The Grignard reagent is one of the most important tools a chemist has. It gives them a super reliable way to build new carbon-carbon bonds, which is kind of the holy grail for building molecules. Seriously, think of it like a set of molecular Legos. It lets you build bigger, more complex, more useful molecules. It's a foundational technology, and it was all born from one of these compounds.
But there's always a but, isn't there? This family has a much darker side, and it's perfectly represented by a compound like DDT. For a while, people thought it was a miracle pesticide. It saved millions of lives from insect-borne diseases. But its incredible stability, the very thing that made it so effective, came at a terrible, terrible price for the environment.
See, the problem with DDT is that it's what we call a persistent organic pollutant. It just doesn't break down. It sticks around, building up in the fatty tissues of animals all the way up the food chain. And it's not alone. Remember CFCs or freons? They were in our refrigerators and spray cans. Turns out they were systematically destroying the Earth's ozone layer. And get this statistic is just staggering. A single chlorine atom from one CFC molecule can destroy up to 100,000 ozone molecules. 100,000.
So, from Nobel Prize-winning tools that help us create to agents of massive environmental destruction, the legacy of these halogen derivatives is all about immense two-sided power. They're a stark reminder of how one tiny chemical change can have world-altering consequences, for good and for ill. Which really leaves us with one final big question. Having learned these very hard lessons, what will we choose to build with this reactive family next?